Okay, so based on the questions that you all sent me, we're going to go through some review topics for the final exam. I would say the majority of these questions are Organic 1 topics, and then there's some Organic 2 stuff at the end. I've tried to pare this down, so it's just things that are pretty relevant for the exam. It's certainly not all-inclusive. There's a lot of topics I'm going to try to get through, so I'll be moving pretty quickly, but of course you can pause the video and take some time to think about some of the things as needed. To determine the hybridization of an atom, we're going to be looking at the number of groups around that atom. And first, to understand what groups are, a group can be a bond, and it doesn't matter if it's a single bond, a double bond, or a triple bond. Those all count as just one group each. A lone pair counts as a group. Positive charges do not count as groups. And the reason this information is useful is because it can tell us not only the hybridization, but the bond angle and the geometry. So let's look at a few examples here. First, say we want to determine the hybridization of this oxygen. When you're looking at something like this, the first thing you want to do is draw in any lone pairs that aren't shown. So for this oxygen to have its octet, it should have 2 lone pairs. So now if we count the number of groups, we have 2 bonds, 2 lone pairs, that's 4 groups around the oxygen. 4 groups is sp3. And that tells us that oxygen has 109.5 degree bond angle, and at least the geometry for all the electrons around the oxygen is tetrahedral. In this next one, say we want to look at the hybridization of the nitrogen. For it, there's no lone pairs because we have an octet of electrons already around it. So now we just need to look at the number of groups. Each single bond here is a group. The double bond is a group. The positive charge doesn't go into our determination for hybridization. So with this, there's 3 groups around the nitrogen. 3 groups is sp2. And that nitrogen has a trigonal planar geometry. Right, our last example here is a carbocation. And what you want to think about if you see a carbocation, if we just start with the original structure, we know that there's 2 hydrogen on this carbon. So carbon has its 4 bonds. The positive charge takes the place of one of those hydrogen. So now there's only 1 hydrogen there. So when we go to count the groups, we have 1 bond, 2 bonds, 3 bonds. There's no lone pair there because the carbocation is a void of electrons. So that carbon is electron deficient. It has less than an octet. 3 groups. That carbon is sp2. As we built on our model of hybridization, we learned that it's really important to pay attention to resonance structures. And if the atom you're looking at for hybridization is involved in resonance, you really need to look at it carefully to figure out hybridization. So for example, in this first structure here, this oxygen has 2 lone pairs. So we have the bond to the carbon, the bond to the hydrogen, the 2 lone pairs. That appears to be 4 groups, and it appears sp3. But you always want to think about resonance. And in this case, we have the lone pair next to the double bond, and we can draw a resonance structure for this. When we do that, we get this. We used one of those lone pairs to make the pi bond, one still remains. So now if we look at this and count our number of groups, we have the double bond, the single bond, the lone pair, 3 groups is sp2. So when you have this type of system where there's multiple resonance structures that give you different hybridizations of an atom, pick the one with more S character. So sp2 has more S character than sp3. In the second example, it's fairly similar. It's just now that there's a positive charge instead of a pi bond next to the lone pair. So that nitrogen does have a lone pair. We can draw a resonance structure where that lone pair moves in to form a pi bond. Here's the other resonance structure. Now, if we look at the hybridization for this, and it would probably help to draw in the bond for the NH, so I'll do that. Count our number of groups, bond, bond, bond. There's 3 groups. That nitrogen is sp2. And if you're given a question like this, it doesn't even matter if you're given the first resonance structure and pointing at that nitrogen, you would classify that as sp2. We're going to take a look at how you classify a molecule for acidity and do some comparisons, and there's some general rules to follow. And you basically follow these in order. So first you look at the atom directly bonded to the acidic hydrogen. If the atom, if you're comparing 2 things, the larger atom will have a more acidic hydrogen. Next, a more electronegative atom will have a more acidic hydrogen. Then if, say, the atoms are the same that you're comparing, you can analyze the rest of the structure, and you can look at conjugate base stability. So if the conjugate base is resonance stabilized, that makes it more acidic. Nearby electronegative atoms make it more acidic. Remember, this is called the inductive effect. And then finally, if you're looking at hybridization, an atom bonded to the hydrogen, if that atom has more S character, it's going to be more acidic. So let's put this into practice for a couple of examples here. So if we're going across the periodic table, we're in the same row here, going from hydrogen on a carbon to on an oxygen, we're increasing electronegativity. So OH is more acidic than CH. Next, if you go down the periodic table, oxygen's a smaller atom, sulfur is a larger atom. That makes the proton on the sulfur more acidic. So here we're increasing size. So of these, the thiol would be the most acidic, followed by the alcohol, and then the methyl hydrogen. So that's the atom effect. In this next comparison, we're looking at a proton that's on a carbon in both cases. So in both cases, we have a carbon and a carbon. So now we need to look at a more remote effect, and in this case it helps to draw the conjugate base. So if you lose the hydrogen, or lose the proton H+, you have the conjugate base with a negative charge. Comparing these two, The one on the right, that negative charge is just stuck on the carbon. It's not delocalized. The one on the left, this negative charge is delocalized through resonance. Delocalized means it's more stable, making the acid that it came from more acidic. So that's your resonance effect. And then in these final two, again, we're looking at the same atom in both cases, carbon and carbon with a hydrogen, but this is analyzing the S character. In this first one, the carbon is sp2. And don't forget, there is another hydrogen on that carbon that's implied. On the alkyne, the carbon is sp. So the S character for sp2 is about 33% S. In sp, it's 50% S. So that has more S character, and the alkyne CH is more acidic. While we're at this example, I want to show you a really common exception that doesn't so much follow this typical trend, but it's really important to know. If you're asked to compare an amine, I should say the hydrogen on the amine nitrogen, versus an alkyne CH. If you follow these rules in order, you would get to the atom effect and say, well, I'm comparing a carbon versus a nitrogen. Nitrogen's more electronegative, the amine should be more acidic. In this case, in this exception, the hybridization of the carbon being sp kind of takes priority over the sp3 nitrogen. Usually that's not going to be the case. This is just an exception here, and the alkyne is more acidic. In fact, the pKa of the alkyne is about 25. The pKa of the amine is about 35. So a pretty large difference. Let's say you're given this molecule and asked to rank the protons that are highlighted from most acidic to least acidic, so 1 through 5. So you really want to apply your rules in order and thinking of the atom effect first. So basically just think across the periodic table. And we'll add in also the sulfur that's below the oxygen. So here, in terms of acidity, look at first the atoms that the protons are attached to. We have a carbon, nitrogen, sulfur, oxygen, sulfur. So of these, we're going to go from carbon, nitrogen, oxygen, and sulfur. So we can first use our electronegativity trend across the periodic table and say the proton on the carbon will be the least acidic. So let's make that 5, followed by the one on the nitrogen, that'll be a bit more acidic, 4. And then the one on the oxygen will be 3. And then we have sulfur and sulfur. So that will be 2 and 1. So now if we compare these two sulfurs, one has this electronegative fluorine attached nearby. That's an inductive effect that makes that SH a little bit more acidic than the other. So we would say this one is 2, this one is 1. This semester we spent a lot of time looking at alpha protons and deprotonating at the alpha position to form enolates. So it's important to have an understanding of the acidity of alpha protons. So a couple general trends to know, and this list here is ranked from the most acidic to the least acidic. So a couple things to know is if you have an alpha proton between two carbonyls, that's going to be more acidic than just an alpha proton next to one carbonyl. So that's what we have here. Another thing to know is that if we look here at the upper extreme, the alpha proton of an ester has a decreased acidity. And the reason for that is because the lone pair on the ester is dumping electrons toward that alpha proton, decreasing its acidity. And then finally, we'll make this comparison between aldehydes and ketones. So because the aldehyde hydrogen is very slightly withdrawing, aldehyde alpha protons are a bit more acidic than ketone alpha protons. So with this little bit of information, we can make a lot of assessments in terms of alpha proton acidity. So that's what we're asked to do in this example here. And what you want to look at first is the fact that for alpha proton 1 and 4, those reside between two carbonyls. So those are going to have an enhanced acidity compared to 2 and 3. Now, if we just want to break those two down, you can see that 1 has an aldehyde, 4 is just basically two ketones. Well, we know that aldehydes are more acidic than ketones. So we can go ahead and say this alpha proton is the most acidic. Next, we can say 4, because it is still between two carbonyls. We'll rank that as number 2. Now we're down to 2 and 3. And then we look at the nature of these two. So 2, we just have a carbon and a carbon, so that is a ketone. 3 is an ester. Esters are less acidic than ketones. So the ketone is going to be number 3, the ester number 4, least acidic. Let's cover some basics of Newman projections. And what you want to keep in mind about a Newman projection is that you're basically looking at the molecule from one side. So here's your eye looking at that molecule, and you're looking across a single bond. So let's say we're looking across this bond here, and as we're looking in this direction, we have a front carbon and a back carbon. So when we draw the Newman projection, we want to draw the back carbon as a large circle. The front carbon, just make a dot. So then we need to put these groups in our Newman projection. And to help us keep track of things, I'm just going to label, and we have our methyl group. We'll make that A, B, and C. So on our front carbon, the methyl group is in the plane pointing up. So what we want to do is draw that straight up off of that front carbon. And I'll label that A. All right, from there, we need to put B and C in the projection. And the easiest way to think about this is think about just a stick man looking at this structure. So if you're laying there on that page looking from that side, your left arm is going into the page, your right arm's coming out of the page. So proton C is back, that'll be on the left, proton B is out, that will be on the right. And we draw those coming off of the front carbon like this. So again, we found that B is on the right, C is on the left. Now we need to add the groups on the back carbon. So let's label those as well. I'll make the methyl D and hydrogen E and F. So the methyl group is straight down. So coming off of the back carbon, put your methyl group straight down. And then our hydrogen will be like this, because they're pointed out and back, but kind of upwards. E is the wedge, like a right arm, so E is on the right. And F will then be on the left. So when you're trying to analyze this Newman projection, we can do so based on the relative location of these two methyl groups. These two groups are 180 degrees apart. Here's one, here's the other. This is the staggered conformation. And because the methyls are on opposite sides, it's anti. And this is the most stable conformation, because your biggest groups are furthest apart. Now, another conformation we could have that is still staggered is, let's say we rotate the front carbon so that I'm going to put the methyl here, this hydrogen here, this hydrogen here. So we're rotating that front carbon around. The back carbon I'm going to leave the same. So there's the back unchanged. And here's the front. Right, now we have these two methyl groups. They're closer together. The atoms on the front and back are still staggered. But now this is called a ghost conformation. And this one is a little bit higher in energy. Higher energy, less stable. And then I'm going to show you one more extreme, where what if we put the atoms on the front carbon directly in front of the atoms on the back carbon. So basically moving them so that they're right in front. Now we can't draw them on top of one another and still be able to visualize them. So what we do is kind of skew them to the side. But I'm going to leave the back exactly the same. I'm not going to worry about putting my letters in this time. The front carbon, again, really I should be drawing this right on top of here, but that's hard to see. So what we do instead is just skew it to the side slightly. Now, because those front atoms are in front of the back atoms, this is eclipsed. And because we have our largest group, these methyls, in front of one another, and also even these hydrogens being eclipsing raises the energy, but most importantly, these great big groups are on top of one another. That's very destabilizing. This is the highest energy conformation of butane. And this is the least stable. So what you want to avoid is bulky groups being close to one another. A chiral center is an atom that has 4 different groups attached. Usually we're just looking at carbon, but in the case of this molecule shown, don't forget about implied hydrogen. So that counts as a group. I'm going to draw that hydrogen in. And it doesn't have to be 4 different atoms attached. So in this case, the fluorine is a group, the hydrogen is a group, and then sometimes people will get confused and say, well, we have a carbon and a carbon, those aren't different. But you can look out the chain and find points of difference. So here we have an ethyl, here we have a propyl. Those are different things, they can be differentiated. So this carbon is a chiral center, and we designate that with an asterisk. When you have this chiral center, this is a chiral molecule. Not always, but generally when there's one or more chiral centers in a molecule, the molecule is chiral. And if it's chiral, we can draw 2 mirror image forms, but they're different. So I'm going to keep my carbon chain the same, just like this. But then I'm going to give 3D to the hydrogen and the fluorine. So I'm going to put the fluorine on a wedge, the hydrogen going back on a dash. But then we can do the opposite. We'll keep the chain the same. And instead, I'm going to put the hydrogen on the wedge and the fluorine on the dash. These 2 structures are mirror images. So you can think about if you were to pick this structure up and hold it over here on top of this one, there would be a mirror plane between them. But these 2 things aren't superimposable, because if you tried to set this one on the right down on this one on the left, the chain would line up, but the fluorine and the hydrogen would not. So the relationship between these 2 molecules are called enantiomers. So enantiomers are mirror image structures that are non-superimposable. Now we have a molecule that has 2 chiral centers, one here and one here. You can draw the hydrogens in if you want, or leave them implied. I'm going to leave them implied, but here we would have a hydrogen going back, here a hydrogen coming out. This molecule has some different stereoisomers. The first is the enantiomer. And there's 2 ways to draw the enantiomer. One, which I think is probably the easiest, is just to invert the chiral centers. So leave the chain just as it is. And the first chiral center, we put the methyl back instead of out. The second chiral center, we'll put the OH out instead of back. The other way you can do it is, think about a mirror here and draw the mirror structure of this. If we do, there's the mirror of the chain. Here's the OH. Here's the methyl. Both methods give the enantiomer, and these 2 molecules are 100% identical. Because if you take this molecule on the top, I'm going to highlight a reference point here. If you flip this over horizontally in the page, that carbon will come to here. And when you flip that horizontally, the OH ends up going from back to out, the methyl from out to back. So it doesn't matter which method you use to draw the enantiomer, you get the same structure. Now, if we want to draw a diastereomer, when you have a molecule with more than one chiral center, you just want to invert one or more, but not all. Of your chiral centers. Because if you invert all of them, you make the enantiomer. So we can draw a couple different diastereomers. Let's say we decide to invert the methyl. We'll leave the OH as it was in the original molecule. Or you could do the opposite. Keep the methyl as is and invert the OH. This structure A, B, and C are all diastereomers of one another, and they are three different structures, three different molecules. In meso compounds, we have kind of that weird scenario where a molecule has chiral centers, but it ends up being achiral. And the reason for that is due to symmetry. So in these two, on the first one, let's look at it. We have a chiral center here, a chiral center here. Generally, when you have two chiral centers, the molecule will be chiral. But in this case, because we have a symmetry plane that cuts this molecule in half, that makes this an achiral molecule. And it's called a meso compound. And if you try to draw the enantiomer, if you try to draw the mirror image, let's do that. So let's say here's a mirror plane, and I want to draw the mirror image. The mirror image is 100% identical to the first structure. An enantiomer would be non-superimposable. This is superimposable, so it doesn't have an enantiomer, which is why the molecule is achiral. In the second example, we have a chiral center here and here, but again, there's a symmetry plane that cuts through this, rendering this molecule achiral as well. If it's achiral, it does not have an enantiomer. When you have a chiral center, you want to be able to assign its R&S configuration. And for a simple molecule with one chiral center, one enantiomer will be R, the other enantiomer will have the S configuration. Our general rules for doing this: find your chiral center. In this case, it's right here. And you have to be given a 3D to be able to do this. So if you were just given this molecule without 3D, you could not assign the R&S configuration to the chiral center. That's ambiguous. So we find our chiral center, then look at the 4 atoms attached to the chiral center. So that's carbon, carbon, hydrogen, and bromine, and prioritize those by atomic number. The higher the atomic number, the higher the priority. So we can say bromine is priority 1, hydrogen's priority 4, and then carbon is in the middle. Right now, if we're tied, You can move out an atom and compare, but in this case, we can compare directly on just the attachments. So the carbon on the left has a carbon attached and 2 hydrogen attached. The carbon on the right has 2 carbons attached to it and 1 hydrogen. So 2 carbons are better than 1, so this carbon on the right gets priority. So that is number 2 and number 3. The next thing we need to do is rotate this so that priority 4 is back. And what I like to do when you have a slightly more complex molecule, redraw just your tetrahedron, so your 2 end plane bonds, your wedge, your dash, add the priority numbers, 3, 2, 4, and 1, and this becomes a bit simpler to work with. Now, in order to get 4 to the back, you could flip this over. That's one method. Or you could hold one group constant and rotate the other 3. Either way, you'll get the same answer. So here, what I'm going to do, I'm just going to hold 2 in place, and then I'm going to rotate the other 3 atoms. So I'll rotate 4 to here, 1 to here, 3 to here. And we do that rotation. Remember 2, that did not move. But we put 3 out on the wedge, 4 in the back, 1 in the plane. Now we have 4 back, which is what we want. We're ready to assign our configuration. So just draw an arrow from your priority 1 to priority 2 to priority 3. If your arrow goes to the right, as this one does, it's R. If it goes to the left, it's S. So that's R. And in our original molecule here, that chiral center has the R configuration. Fischer projections tend to be kind of tricky for people, and I'm just going to go through a very highlight review of this. So I'm not going to go through all the details specifically. One of the more difficult portions is converting a molecule from a typical bond line structure into a Fischer projection. That's not something you're going to have to do on the final, so I'm not going to cover that. But there's a few things to keep in mind. So there's a very specific definition for a Fischer projection, and you might have just a simple Fischer projection with 4 atoms, or something more complex like we have down here. The cross on a Fischer projection is generally a chiral center. So here we have 3 chiral centers. Now, occasionally you might see one that has, say, 2 hydrogen, in which case it wouldn't be a chiral center. But then by definition, horizontal bonds are pointed out, vertical bonds are pointed back. So in my structure here, these horizontals are out. So those are actually wedges. The verticals are dashes. And the same is true for the Fischer projection I had down here. So you could think of this as all of these horizontals being wedges, all of the verticals being dashes. And that is, by definition, the directionality of those groups. So I'm going to erase those just to keep it from being too cluttered. just to kind of give you an idea of how this Fischer projection translates into a bond line structure, your main vertical chain is going to be in sort of this pseudo-cyclic orientation. That way, no matter which of these carbons you look at, like if you're looking in this direction, the two bonds in the plane are pointed away from you, the viewer. Or if you look here, the two bonds in the plane are pointed away from you, and the same is true here. You can also see how all the groups on one side, when it's in this form, are going to be dashes or wedges. So the bromine, OH, and hydrogen are all on the right. They're all on the wedge in this structure. But this only works when you have your main ring drawn in this pseudo-cyclic pattern. It doesn't work if it's in the zigzag form. But again, don't focus too much on that aspect of this. So what you do want to be able to do is identify stereoisomers of Fischer projections. So for example, we can draw the enantiomer of this. By just inverting the horizontal groups at the chiral centers. So if I draw the enantiomer, let's draw our main vertical chain. There's the CH3, the CH2OH. Here's our three chiral centers. We don't need to put in the dashes and wedges because they're already there by definition. So now we just invert those groups, Br and H, OH and H, H and OH. So that is the enantiomer. We can also draw a diastereomer by inverting one or more, but not all of the chiral centers. So let's say we just maybe invert the first two. Invert those two. We'll keep the one on the bottom the same. That is a diastereomer. So knowledge of Fischer projections becomes important when you start to study amino acids and carbohydrates. Especially carbohydrates in their acyclic form are usually drawn as Fischer projections. We're going to see how to assign E and Z configuration. And if you have a good hang of assigning RNS configuration, you should be pretty good to go for E and Z. What you want to do is look at each carbon of the alkene independently. So we'll look at this carbon first. We'll look at this carbon second. So looking at the carbon that I've highlighted in blue, we want to prioritize the two groups. We'll use the same rules we did for RNS. In this case, they're both carbons, so they have the same atomic number, but look and see what is connected to each. The one on the bottom, we have two hydrogens and a carbon, so CHH. The one on the top, we have a hydrogen and two carbons. Two carbons beats one, so that carbon on the top is priority 1. The carbon on the bottom, priority 2. Now we'll look at the other carbon of the alkene. This one's a little easier. We have fluorine and carbon. Fluorine has a higher atomic number, so it's 1. The carbon's 2. Then, if you have trouble seeing the plane you need to look at, just draw a long line passing right through your double bond. Then look and see where your priority 1 groups fall. 1 is on this side of the line, 1 is on the other side of the line. They're on opposite sides, so that is the E configuration. This is an E alkene. If they were on the same side, it would be the Z alkene. In substitution reactions, there's 2 main mechanisms, SN1 and SN2. SN1 is unimolecular, meaning there's only 1 molecule involved in the rate determining step, but that results in a 2-step reaction. SN2 is bimolecular, both things are involved in a single reaction, so it's 1 step. SN1 involves formation of a carbocation. So let's look at an example of an SN1 reaction. Say we have this. We need a good leaving group. That could be something like a halogen or a tosylate's a good leaving group as well. And then we need a nucleophile. For SN1, you can have strong or weak nucleophiles. Most commonly, we see weak nucleophiles in SN1. So maybe something like methanol. It's a weak, neutral nucleophile. With SN1, what happens, the nucleophile does not get involved in the first step, which is rate determining. We lose the leaving group. And form a carbocation. And you need to be able to form a relatively stable carbocation for SN1. In this case, it's tertiary. Secondaries we can form, not primary, but also allylic and benzylic can be formed. Once you get the carbocation, now the nucleophile can get involved. We use the lone pair on the oxygen. That attacks the carbocation. In this case, because it was neutral, once we add it, you still have that proton attached. So to get to the final substitution product, we just need to take that proton off of there. And there's your product. So the net result is that it's a substitution, meaning we substituted the leaving group bromine with the nucleophile, the methoxy group. One thing with SN1 to always be on the lookout for is carbocation rearrangement. So I always recommend drawing your carbocation intermediate to see if it can rearrange to become more stable. So say maybe you had this secondary carbocation. What's going to happen, in this case it would be a hydride shift. The hydrogen on the neighbor would shift. You don't have to draw the hydrogen in, but you can if you want. That shifts to that position and leaves the carbocation here, and now it's tertiary and more stable. So carbocation rearrangement can and will occur if it can make a more stable carbocation. For SN2, everything happens in a single step, and substitution hinders the reaction. So the rate decreases with substitution. So the fastest SN2 would be with just a methyl halide. And then you could have a primary. Secondary works, but it's going to be slower. So for SN2, you really need a strong nucleophile that, for the most part, these are negatively charged nucleophiles. So let's look at an SN2. Maybe we use tosylate as our leaving group this time. And I'll use the methoxy counterpart to our SN1 reaction. Instead of methanol, we can use sodium methoxide. Break that up, we have sodium plus, OCH3 minus. That's a strong nucleophile and a strong base. So now this can directly attack that carbon. You lose your leaving group. Here's our new bond to the OCH3. And then we lost OTS minus. I'll just throw the sodium over here to kind of pair up with it. In SN2, there's no carbocation, so you do not have to worry about rearrangement. Now, elimination reactions, they're kind of the counterpart to substitution. They are in competition with substitution. I'm not going to say that's going to be a huge aspect of the exam, so I would say, don't worry too much about the two as competing reactions. Just be able to predict substitution and elimination products and know the basics. For elimination, at least E2, we require a strong base and a proton that's beta to the leaving group. Also, heat helps to favor elimination over substitution. So in this example here, we have our leaving group, which is the bromine, and that is on what we call the alpha carbon. And then carbons next to the alpha are beta carbons. This molecule has 2 beta carbons, and each beta carbon, in this case, does have beta hydrogen. So we can think of elimination products eliminating from each beta position. So let's do the one on the left first. If you use the base hydroxide, that will attack the beta hydrogen. Those electrons will come down to form a double bond between the alpha and beta position, and you lose your leaving group. So there's the product. Now, what if we do the same thing with the other beta hydrogen? So let me redraw this. Now we're going to use this beta hydrogen on the right and do the same thing. So there's alpha and beta. Attack that and eliminate. And there's the product. So when you have multiple products that can form, in general, when you use a small base like hydroxide or an alkoxide, the major product is the more substituted double bond, and that is called the Zaitsev product. So in this case, the double bond for the first product has 1, 2, 3 carbons attached. That's tri-substituted. Versus the double bond below has just 1 carbon attached. That's mono-substituted. This one is the more stable alkene. and this is the major product. If you do use a bulky base instead of a small base, like tert butoxide, here's NaOTBU, and if we draw this out, we have O- with the tert butyl group. This is a bulky base. This will give the Hofmann product, which is the less substituted alkene. So what we do is find the less substituted beta hydrogen to do the elimination. And in that case, it's going to be the beta hydrogen at this position. So the base can grab that more easily than the more hindered beta hydrogen on the left side. It'll eliminate. And there's the major product in this case. We're going to review some alkyne reactions. And these reactions will work for at least HX addition, will work for terminal and internal alkynes. Usually don't use HF. And what we're doing is adding the acid across the triple bond. So don't forget there's a hydrogen on the end here. And when you add HBr across this triple bond, we can think of it as H plus and Br minus. And this will follow Markovnikov's addition, meaning the hydrogen will go to the side where there's more hydrogen. So the hydrogen will add here, the bromine will add here. And the mechanism for the alkyne reactions, Br adds, and that comes and grabs the proton. We go from the triple bond to the double bond. We have the bromine. There's the new hydrogen that's added. Here's the old hydrogen. So if you just use one equivalent of HBr, that's the product. If you were to use an excess or two equivalents, say we add more HBr, this would still follow Markovnikov's addition. The hydrogen would go to the side where there's more hydrogen. We go from the double bond to the single bond. Here's the new hydrogen and the new Br. Next, we're going to look at hydration of alkynes. In this case, we're using a terminal alkyne. So a couple things about terminal alkynes. Again, it follows Markovnikov's selectivity. That also requires the mercury catalyst. Mercury 2. If you used an internal alkyne, maybe something like this, you could do the hydration with just H2SO4 and water. You don't need the mercury. So to do this hydration, what we're effectively doing is adding H and OH across the triple bond. Again, following Markovnikov's pathway, we'll add the hydrogen to the side where there's a hydrogen. We'll add the OH to the more substituted carbon. We're not going to go through the mechanism, but we go from the triple bond to the double bond. Because the double bond isn't linear, I draw it in this zigzag pattern now. I'm going to put the OH here, and then the hydrogen here. And just to clean this up a little bit, I'm going to leave those hydrogen implied. So let's just draw the double bond and the OH. What we formed here is an enol, where we have an OH attached to an alkene. The enol does not hang around long like this. The equilibrium quickly pushes to the more stable carbonyl. This is called tautomerization. And the easiest way to draw the tautomer, get rid of the double bond on the alkene and make the OH a double bond O. So we go from the enol to the ketone, and that's the major product of this hydration. The counterpart to the hydration is the hydroboration, which the main key point to this is it's anti-Markovnikov. So again, we have a terminal alkyne, so we do get selectivity here. But because it's anti-Markovnikov, the hydrogen goes to the more substituted carbon, the OH to the less substituted carbon. When we draw the product of this, we get an enol, and we'll add the hydrogen here and the OH here. Again, if you want to draw this without the implied hydrogen, that's perfectly fine. Again, because we have the enol, this will tautomerize, and tautomerization is really just an adjustment of equilibrium. So the equilibrium will predominate to give the carbonyl. So like we did before, erase the double bond and make the OH a double bond O. And when you tautomerize this terminal enol, we end up with an aldehyde. So the hydroboration of terminal alkynes gives aldehyde products. The alkylation reactions are exclusive to terminal alkynes because you have to have this acidic hydrogen on the end to do this alkylation. So what happens is you first treat this with a base. You could use NaNH2. Sometimes you'll see sodium hydride used. But the base deprotonates the alkyne. And we get a negative charge here. This is a really good nucleophile. So then what that will do is react with the organohalide. Here our organohalide is ethyl bromide. Let's just draw it in green so we can, I'll draw it here in green so we can keep track of the new atoms. Now this negative charge attacks the carbon with the leaving group. We lose the Br, the bromide. This is just an SN2 reaction. And now what we've done is we've added the ethyl group to the alkyne. And you can do any of those alkyne reactions we talked about before with this. Just to review a couple others we didn't talk about, let's look at the reductions. So if you use hydrogen gas and Lindlar's catalyst, that will reduce the alkyne to a cis alkene. So what that means, we'll have our ethyl group on one side, the propyl group on the other side, in a cis relationship. If you want the trans alkene, you can use the dissolving metal reduction, solid sodium, liquid ammonia, low temperature, and that will reduce to the trans alkene. When we talk about radicals, we're talking about an unpaired electron. And for example, if you have CH3 minus, that has a lone pair on the carbon. But if you have the methyl radical, you would have CH3 with a single electron. That's an unpaired electron on the carbon. There's a couple different reactions we can do involving radicals. One that you're probably most familiar with is a radical halogenation, where a hydrogen is replaced by a halogen. And the position halogenated is really based on when a hydrogen gets abstracted, what gives the most stable radical. And radical stability follows the same trend as carbocation stability. So what that means is resonance stabilized radicals like benzylic and allylic are the most stable, followed by tertiary, secondary, and primary would be the least stable. So let's say we did the radical bromination of ethyl cyclohexane. What you want to do is find the most substituted carbon that has a hydrogen, because a hydrogen is abstracted in the first step. So in this case, it's this tertiary carbon. We're not going to go through the mechanism, but I will show you the intermediate. So this hydrogen gets abstracted, and you get a radical there. And then that radical abstracts a bromine from Br2. So I will show the arrows for this. So we take that electron, pair it with one of the electrons with the bromine, the other gives a bromine radical. A reaction that is nearly identical yet uses a slightly different reagent is NBS. And this basically provides a source of Br2. There's more subtle details than that, but that's the important thing to keep in mind. This is most commonly used for allylic and benzylic brominations. And what you do is look for hydrogen at the allylic or benzylic position. In this case, that would be the two hydrogen here. One of those is abstracted to give you, this would be a benzylic radical, which is extra stable because it's resonance stabilized by the benzene ring. And then that will take a Br from Br2, give you the benzylic bromination product. Another radical process that is quite common is addition to alkenes. And this often leads to polymerization reactions. So this involves a radical initiator. And a common initiator is hydrogen peroxide. So what basically happens here, here's peroxide. This peroxide bond breaks quite easily to give you two of these hydroxy radicals. This can then add to an alkene. So here's our alkene involved, and in general, this will add to the less substituted carbon because that gives us the radical with the more substituted carbon. So to show you what I mean, here's the OH radical. Think of 2 electrons in the pi bond. This will pair with one of those and add the hydroxide to one side. And then the other radical will end up on that more substituted carbon. So that's why the OH went to the less substituted carbon there. So we add that, and we get a radical. Now, I don't want to go way into polymerization, but the way a polymerization would then work is now this is your radical species, and this could react with a second molecule of alkene, really in a similar mechanism to the first, where that adds there. There would be our new bond. I'm going to put these two carbons just kind of down out of the way. Can't forget our OH there. So we've added that, and we generate a new radical, and that would continue to polymerize that alkene. NMR is quite a detailed, lengthy topic that I'm really going to try to condense here in just a few slides to give you the basics. We're going to look at proton NMR. So this is showing us the protons in the molecule, the hydrogen. Every chemically distinct proton in a molecule gives rise to an NMR signal. So if we look at this molecule here, I'm going to work it from right to left. We have a methyl group. That CH3 is one type of proton. There's no hydrogen at the carbonyl carbon. Then we have a CH2 group. That's another type of proton. We have another CH2 group that's a different type of proton. So why aren't the two CH2s equivalent? Well, one is close to a carbonyl, one's close to an isopropyl. They're in different environments. They can be differentiated. Moving on down, we have this CH, which is D, but then that carbon has two methyl groups coming off of it. Those two methyls are attached to the same carbon. They're completely equivalent. So those would both be E. So this molecule here would have 5 proton NMR signals. And then those signals are split by the neighbors. So what that means is you count the number of protons on the neighbor and add 1 to that. So if we work through this one, if we look at this carbon, here's its neighbor. The neighbor has 0 protons. 0 plus 1 is 1. So that is just going to be a single line, which is called a singlet. Okay, now let's look at this carbon, or the protons on that carbon. On its neighbor, there's 2 hydrogen. So we take 2 plus 1 is 3. The signal for that one will be split into 3 lines, or a triplet. So a triplet looks kind of like that. Next, let me redraw this so we're not writing on top of things we've already done. Let's look at the signals for this proton. So you want to look at the neighbors. We have a neighbor here, a neighbor here. The neighbor on the right has 2 hydrogen. The neighbor on the left has 1 hydrogen. So the total number of neighbors is 3. 3 plus 1 is 4. That's a quartet. A quartet looks kind of like that. Okay, now let's look at the hydrogen on this carbon. Right, so here we have neighbor here, here, and here. This would be 3 plus 3 is 6, plus 2 is 8. So 8 neighboring protons, 8 plus 1 is 9. That would be split into 9 lines. 9, we just call that a multiplet. And then finally, we have the signal for the CH3 groups here. You only need to look at one of them to figure this out because they're equivalent, so they give the same signal. So let's say we're looking at these protons on this carbon. Here's the neighbor. The neighbor has 1 hydrogen. 1 plus 1 is 2. That'll split into 2 lines, or a doublet. So a doublet's just kind of like that. So that's the 4 types of signals that you would see in the NMR spectrum. The next thing you have to consider is, once you know what signals you're going to have, where do they show up? And for proton NMR, they show up usually in the 0 to 12 parts per million range. And it really depends on the environment that they're in. If they're just regular, sp3 carbons, they usually show up up toward the right end of the spectrum, which is called upfield or shielded. So the upfield region of the spectrum, shielded protons. The left end is downfield and deshielded. If the proton is next to a carbon with a double bond, that falls in the allylic region. If it's on a carbon containing a heteroatom like oxygen, nitrogen, or a halogen, that shifts it downfield to about between 2 and 5. If it's directly on a double bond, that's in the vinyl region. If it's on an aromatic ring, it falls in the aromatic region. Then we have aldehydes and carboxylic acids. Alcohols and amines can show up anywhere. And they usually show up as a singlet. Typically, alcohols and amines don't split. So if we want to apply this to our example down here and figure out where these signals go, we need to figure out the different protons involved. So we have protons here, that's type A. Hydrogen here, we'll make that B. CH2C, D. The OH will be E. And monosubstituted aromatic rings often just show up as a multiplet in the aromatic region. So we're going to just draw that as one big chunk, F. So it's all about the environment. A is just a CH3, nothing all that special. So A is going to appear down here in the saturated region. B is on a carbon next to an OH. So that's going to fall in the electronegative region. So let's stick that in there. C is a CH2. It's really not in any predominant region. It might have a little bit of a pull from the OH, but not much. So we're going to put it down there very close to A. There's C. D. D is a CH2, but it's next to this double bond. Because of that, we're going to put it in the allylic region. So I'll put D here. F is the aromatic ring. We'll put that in the 6.5 to 8 region. And then E is the OH. Again, it can show up anywhere. I'm just going to throw it here around 5 because that's a nice open space. Now, it would probably be good practice if you go through and try to assign the multiplicities or the splittings to each of these. I will go ahead and draw in and kind of fill in the spectrum so you would know what it looks like. So here's how the spectrum for this one might look. A, we would expect to be a doublet. B would be a sextet. C would be a quartet. D would be a triplet. E, which is the OH, I drew that as kind of a broad singlet. And F is this multiplet for 5 hydrogen, which is the aromatic ring. I put the integration numbers above each signal, which tells us how many protons each one corresponds to. So here's an example of how we might work through a proton NMR. In this case, we are given a molecular formula. So the first thing you want to do is figure out the number of unsaturations, which will tell us the number of rings or pi bonds. Use the formula 2 times the number of carbon plus 2 minus the number of hydrogen minus the number of halogens plus the number of nitrogen divided by 2. So in this case, we have 2 times 5 carbons plus 2 minus 12 hydrogen. There's no halogen, no nitrogen, oxygen we ignore. Divide that by 2. So we get 12 minus 12 divided by 2, 0. There's no unsaturations here. So no rings, no double bonds. From here, what you want to do is go through and try to identify fragments on your spectrum. Do that by the number of hydrogens. So the way I would do this, I say, here's a peak for 2 hydrogen. Let's make that a CH2. Here's a peak for 1 hydrogen. Make that a CH. Here's a peak for 1 hydrogen. Make that a CH. 2 hydrogen, CH2. 6 hydrogen. Well, you can't have CH6, so if you see something like this, it's usually 2 equivalent CH3 groups. From there, check your work. See if you have 5 carbons accounted for. 1, 2, 3, 4, 5, 6. I made a mistake. I assigned something as a CH that shouldn't be a CH. What else do we have here? We have an oxygen. So maybe instead of a CH, one of these is an OH. And OHs usually don't split, so I'm not going to do that one. But what I can do is cross that one out and make that an OH. From there, I like to go through and just add dots to show how many bonds each thing needs. For example, the CH2, the carbon has 2 hydrogen. It needs 2 more bonds to be a happy carbon with 4 bonds. The CH needs 3 bonds. The OH needs 1. CH2 needs 2. These methyls each need 1. Now use your splitting to help you out. This is split into 3 lines. N plus 1 is 3. N equals 2. That means the neighbor that that's connected to should have 2 hydrogen on it. Well, we're in luck. There's only one option. The CH2. So that works out. Well, now if we look at this CH2's peak or signal, it's a quartet. N plus 1 is 4. N equals 3. Well, it's already connected to 2 hydrogen by this neighbor, so it must need to be connected to something with 1 hydrogen. OHs usually don't cause splitting, so we're going to connect it to that CH. Then if you look at these CH3s, this is a doublet. N plus 1 is 2. N equals 1. Those CH3s need to be connected to something with 1 hydrogen. Well, that's going to be this carbon right here. So let's do that. All right, we're only left with a dot here, a dot here. So let's connect those together. We didn't even really use the chemical shifts here, but the reason that this signal is clear down at about 3.6 is because it's connected to the electronegative oxygen. So let's clean up our structure. So we have OH connected to the CH2. That's connected to another CH2. That's connected to the CH. And that's connected to 2 CH3 groups. So we do that, and we're done. We're going to talk a little bit about the interconversion of carboxylic acid derivatives. And I have this chart of the different derivatives as well as just carboxylic acid included here. And what you want to keep in mind is that the amide is the most stable and the least reactive, and that's because NH2 minus is the worst leaving group. And then that follows a continuum down here to the acid chloride. It is the least stable derivative, and it's the most reactive, and the reason is because of the Cl minus is the most stable leaving group, so it can leave easily. So what we can do is we can convert any of the less stable derivatives into a more stable derivative. So you can convert the acid chloride into any of these. And you can convert, say, the ester into the amide. You can also convert it to the carboxylic acid, but you can't go backwards with just a simple interconversion without finding a special reaction with a special driving force. Now, one thing that I will go ahead and mention, all carboxylic acid derivatives can be hydrolyzed to carboxylic acids. All right, so if we look at this and you're given a reaction to predict, say we take an acid chloride and you react this with NH minus. So now that will act as a nucleophile and add to the acid chloride, and the product you get be the amide and Cl minus. So you want to make sure this reaction is favored. Well, because the amide product is more stable than the acid chloride starting material, this reaction should in fact proceed to the right. The other way you can look at that is just in your nucleophile and leaving group. Cl minus is more stable, N minus is less stable. So the N minus is more reactive, more likely to attack and take you to the amide product. But if you're given, let's say, an ester and asked to react it with an acetate, we can draw the hypothetical product. Like that. But in this case, you're going from something more stable, the ester, to something less stable, the anhydride. So this reaction does not proceed to the right. Instead, it proceeds to the left, or lies to the left. If you're asked to assess carbonyl reactivity, basically what we're essentially asking is, how electrophilic is the carbonyl? Or how likely is it to react with a nucleophile? And our general reactivity order is we have carboxylic acid derivatives and aldehydes and ketones in the mix, even though they do react a bit differently. But the most reactive is going to be the acid chlorides and the anhydrides. And then aldehydes are a bit more reactive than ketones, but still not as reactive as the acid chlorides and anhydrides. Then you have the ketones, and then we're back to carboxylic acid derivatives, esters, and amides, which are the least reactive. The other thing to keep in mind is that conjugation decreases the reactivity, because if the carbonyl is conjugated, that's a stabilizing factor. We have this conjugation here. That makes the carbonyl extra happy, so it doesn't want to react. So if we apply this to our system or our molecule down below, where you're asked to rank these different carbonyls by reactivity, first, let's just identify what they are. We have an aldehyde, we have a ketone, we have an ester, and we have an ester. Then look and see which of these are involved in conjugation. This ketone is conjugated with the aromatic ring. This ester is conjugated with the aromatic ring. So let's make a note. That's conjugated. That's conjugated. So now if we look at these in relation to our reactivity order, the most reactive one on the list that we have in this molecule is the aldehyde. So we'll make this number 1, most reactive. From there, next we have a ketone. That's number 2. Then for 3 and 4, we have esters. One ester is conjugated, one is not. So the unconjugated ester is a little bit more reactive than the conjugated ester. So that'll be 3 and 4, least reactive.